In this video, we're going to do some problems off of page 269, some examples from section 6.2 of our textbook. We're going to start with problems 14 through 22 even, which is about the data summarized here, and then number 26 on the next page. And exercises 13 through 24. Use the data in the table below for pulse rates of adults, males and females, based on data set 1, body data, in Appendix B. Hint, draw a graph in each case. All right, well, starting off in number 14, find the probability that a female has a pulse rate less than 60 beats per minute. All right, we are told the pulse rates are normally distributed, so I know to draw a bell-shaped distribution. I'm asked to consider female pulse rates here, so the mean is 74 beats per minute. And this problem's good because it gives me units, so I'll use beats per minute throughout, and the standard deviation of this distribution is 12.5 beats per minute. All right, find the probability that a female has pulse rates less than 60 beats per minute. 60 is less than the mean by a little bit more than one standard deviation, so just try to put that in there somewhere that makes sense. So I'm trying to find that probability. We'll be using normal CDF in our calculator. So from the left, from minus 10 to the 99, something so far away from 74 beats per minute that's almost impossible. In fact, it is impossible. 0 is the lowest we could think about having a heart beating in beats per minute. But that's so far away, it's like acting like minus infinity, so I'm just going to let that be and end at 60 beats per minute, and this time I need the mean and the standard deviation. Go into the distribution menu, find normal CDF, minus 10 raised to the 99th power, comma 60, comma 74, comma 12.5. All right. Round probabilities to 3 decimal places, 0.131. That's the probability of getting a female whose pulse rate is less than 60 beats per minute. So we'll move on to number 16. Find the probability that a male has a pulse rate greater than 80 beats per minute. So again, a normal distribution. The mean this time, 69.6 beats per minute, and the standard deviation of 11.3. All right, greater than 80 beats per minute. 80's above the mean. Greater than means shade to the right. So I'll be using normal CDF again to find that probability. Let's see, we're supposed to be to the right of 80. So 80 is my left-hand endpoint. Pretending I'm going out to 10 to the 99, which is an impossible heart rate, but I'm just using something so large that it's like going out to infinity. Type in a mean and the standard deviation. Normal CDF, 80, comma, 10 to the 99th, comma, 69.6, comma, 11.3. We find out a probability of 0.179 to 3 decimal places. All right, number 18. Find the probability that a male has a pulse rate between 65 and 85 beats per minute. So still in the distribution of male pulse rates. I do always like writing the mean and the standard deviation below because this is going to help me when I type into the normal CDF, even if it's a bit repetitive. All right, from 65 to 85. 65 is below the mean by just a little bit. 85 is above the mean by quite a bit. So this time, normal CDF. I'm not going to have enough room to write that there, so we'll just come down here where it made more sense to write it in the first place. Normal CDF, 65 to 85, 69.6, and 11.3. The mean and the standard deviation always go in at the end. And we get a probability of 0.572. All right, well, we're doing the ones between 14 and 22, so we just have a few more to go. Let's do number 20. Find the probability that a female has a pulse rate between 60 and 70 beats per minute. All right, this time we're back in the distribution for females. So the mean now, again, 74.0 with a standard deviation of 12.5. And we're asked for the probability between 60 and 70 beats per minute. Well, let's see, 60 below the mean, 70 still below the mean. So like a little slice right there. So again, we'll be using normal CDF. 60 to 70, 74 beats per minute and 12.5, the mean and the standard deviation. And I have a probability of about 0.243. That was number 20, leaving us just number 22 to do before we get to 26 on the next page. For females, find the first quartile, Q1. Well, that is the data value that separates the bottom 25% from the top 75%. So this time, instead of looking for probability, we're asked to find a data value. All right, first quartile clearly below the mean, separating the bottom 25% from the rest. Since we're looking for a data value, that's what inverse norm does. All right. Inverse norm takes that area to the left, always the area to the left, the mean, and the standard deviation. All right, and the data value we get is 65.57 beats per minute. That's the second quartile. That's the 25th percentile. That's the data value that separates the bottom 25% from the top 75%. All right, well, that finishes up the problems about this particular set of data. Number 26 has us investigate heights. 25 and 28 use these parameters based on data set 1, body data, and appendix B. Men's heights are normally distributed with a mean of 68.6 inches and a standard deviation of 2.8 inches. Women's heights are normally distributed with a mean of 63.7 inches and a standard deviation of 2.9 inches. Number 26. The United States Air Force required that pilots have heights between 64 inches and 77 inches. Find the percentage of men meeting that height requirement. So I need to consider the information given to me about men's heights. Mean of 68.6 inches. And a standard deviation of 2.8 inches. All right, and meet this requirement. Well, that's between 64 and 77. So 64 below the mean, 77 above the mean. I don't know how well to scale I just did that, but some region that looks like that. Always a good idea to draw a diagram, even if we don't get it precisely to scale. So this is 26A. I'm looking for a probability, so I'll be using normal CDF. I need to type in a left-hand endpoint, a right-hand endpoint, the mean, and the standard deviation, which I haven't left myself enough room here, but I'll be typing 68.6 and 2.8. So into the distribution menu, 64, 77, 68.6, 2.8. Now I click on the wrong thing again, so let's try that again. Normal CDF. 64, 77, 68.6, 2.8. All right, 0.948. Let's see, what percentage of men meet the height requirement? So 94.8% of men meet this height requirement. If the Air Force height requirements are changed to exclude only the tallest 2.5% of men and the shortest 2.5% of men, what will be the new height requirements? So in part B, we're asked to find new height requirements. The mean, still looking at the distribution of men here. 25 has you use the distribution information given for women. 68.6 inches and a standard deviation of 2.8. We're supposed to exclude the bottom 2.5% and the top 2.5%. So we're looking for data values, the actual heights that separate the bottom 0.025, 2.5%, and the top 0.025. So a data value here and a data value here. Well, the first one, this data value, that's just given to us as an inverse norm problem. Area to the left, the mean, and the standard deviation. Have to be a little more careful for the top bound because 0.2025, that's the area to the right, not the left. So I have to think to myself, well, if 2.5% is to the right, 1 minus that is to the left. That's 97.5% to the left. So that's what I'll have to type in to inverse norm. The area to the left. All right, so 2 inverse norm calculations, that's going to give us 2 heights. I'm going to round these to 1 decimal place when I'm done, just following our typical round off rule. $63.1 and 74.1. So those are the new height restrictions. We'd want to rule out anyone shorter than 63.1 inches and anyone taller than 74.1 inches. And that's it for now.